Hello, my name is Robert Smith, and I'm with New River Community College. And today we're looking at how to prepare a buffer. In this case, we're asked to prepare a carbonate buffer of a specific pH or around that pH. Um, so to do this, we would need to look at the carbonate. In this case, they're asking carbonate, but they can easily ask for phosphate or any number of different types of buffer systems. And for this particular one, carbonate would come from carbonic acid or carbonic acid, where you would have, we have H2CO3. And if you deprotonate it once, or if you dissociate one proton from it, you would get HCO3 minus. And if you do it again, you get CO3 2 minus. So what we would want to do is see how we could prepare this buffer of the specific pH. And in order to do that, we first have to find out what the acid dissociation constants of these species are. So let's investigate. So we have Ka. For our H2CO3, we can get that directly from the book, which would be a 4.2 times 10 to the minus 7. That looks like a pretty good candidate. But let's take a look at one more. The acid dissociation constant for HCO3 minus would be Ka is equal to 4.8 times 10 to the minus 11. So and we don't even have to worry about this last one. So if we did the pKa, which is just the negative log of the Ka, much like pH is the negative log of your hydrogen proton concentration. So the pKa for this one is 6.38. And for the next species, the pKa is 10.32. And what we want to do is we want to select the species of interest will be the one whose pKa is closest to the target pH. So in this case, we're going to pick carbonic acid in particular. This is a technique that you can apply to any polyprotic acid. You could just pick the one whose pKa is closest to the pH. And what you'll end up doing is using the Henderson-Hasselbalch formula. So that states that the pH is equal to pKa plus the log of the concentration of the ratio between the acid that you've chosen and its conjugate base. So it's important that you remember that this is the one that you've chosen, the acid. This one right here. And then the conjugate base is whatever the conjugate base of that acid is. But we're focused on the acid. Okay? So in this case, we know several things. We know that the pH that we're trying to get is 7.80. And we know that the pKa of our acid is 6.38. But we don't know what the ratio between our conjugate base and acid are. Remembering that the acid is H2CO3, the conjugate base would be HCO3 minus. So this is our acid. Let's put that in red. This is our acid, and this is our conjugate base. So if we subtract 6.38 from 7.8, we end up with the 1.42 is equal to the log of the concentration of Cb, conjugate base, over the acid, which would just be the log of HCO3 minus over H2 CO3. And to remove that log, we'll have to raise make every term the exponent of 10 to that power. So we now know that the ratio between HCO3 minus over H2CO3 is going to be equal to 10 to the 1.42 power. So it's pretty big in this particular case. That's approximately 26.3. So if we were to make this buffer, first of all, you can't have free ions. You can't, if you buy a chemical from a chemical company, it won't be a free ion. It will be a salt of some sort. So our ratio between like a salt, like let's say it's sodium HCO3 to H2CO3 would be 26.3 to 1, which means that you would want for every 1 mole of H2CO3, you would want 26.3 moles of NaHCO3. This may be not the best example. You want to, oftentimes what you'll want is pick a buffer solution that's close, that has a pKa that is closest to the value that you're trying to reach as far as pH. So if something like phosphoric acid maybe has a better pH or a better pKa closer to that pH, you may be more inclined to use phosphoric acid so that you're not wasting chemicals. But for the purposes of this hypothetical, this works. So if you want to prepare this in solution, you would get 1 liter of water, simple enough, and put 26.3 moles of NaHCO3 and 1 mole of H2CO3, and you would get something very close to pH of 7.8.